Welcome back, students. This is the session 3 from the chapter of alternating current, and the topic for this session is power dissipation in a resistive electrical circuit. So, here I have made one electrical circuit which consists of a resistor having a resistance of R, and this is connected to an AC source. So, this is basically a pure resistive circuit. And now, I have written here some bullet points here in order to save the time. So when an electric current passes through this resistor, there is a dissipation of electrical energy, which is called the Joule heating, and this Joule heating is given by I square R. That is P is equal to I square R, which, and since we know in the previous session we have seen that I is equal to Im sin omega t, where Im is the current amplitude. So I have put this value of I in this equation. So I got Im square R sin square omega t. Okay, that is I is equal to Im sin omega t whole square. So this will be equal to Im square sin square omega t into R. So this is the instantaneous power which is dissipated in a resistor. Now the average power dissipated over a cycle is given by 1 by T. We have to I will just write it here that the average value of a function, say ft, over a period say t, is given by integration, that is 1 by t, integration from 0 to t f t dt. That is the average value of a function ft over a period say t is given by 1 by t, integration from 0 to this t ft dt. So I have used this this concept here in order to find the average power which is dissipated over a cycle. So the average power dissipated over a cycle will be equal to 1 by t, where t is the time period, and we have to integrate this expression, that is I m square R sin square omega t from 0 to t. So this is equal to I m square R sin square omega t dt, and since I m square R and t, they are constant, so I have taken it out, and so I am left with this equation, that is I m square R divided by t, integration from 0 to t, where t, this capital T, is the time period, and here I have written this expression, that is the angular frequency is equal to 2 pi upon t, where t is the time period. So now what is time period? It is the time period is the time taken to complete one cycle. So one cycle, this omega is equal to 2 pi upon t, or we can say that t is equal to 2 pi upon omega. So now, so this average power, now this average power is depicted by P bar, So P bar will be equal to I square mr. Now, sin square omega t, there is one mathematical expression which is cos 2 theta is equal to cos square theta minus sin square theta. So now, if I put the value of cos square theta as 1 minus sin square theta, so I will be getting as 1 minus 2 sin square theta. So I use this expression in order to write this sin square omega t in terms of cos 2 omega t. That is, if I use this expression here, then sin square omega t, that is, you just substitute the value of this theta by omega t. So what I will be getting is, I will be getting that 2 sin square omega, that is 2 sin square omega t will be equal to 1 minus 2 cos 2 omega t divided by 2. So this is the expression which I have got using this mathematical formula. So I have substituted this value, that is sin square omega t, in this equation. So this is equal to 1 minus 2 cos 2 omega t dt. Now I will be solving this question, this expression in order to find the average value of the power dissipated over a cycle. So here this is the AC source. Now I will just write it here, AC source. Now the instantaneous power P was equal to I square R, and this was equal to Im square sin square omega t. And now I will be solving this equation in order to find the average power which is dissipated over a cycle. So the average power P bar is equal to Im square R divided by 2t. Here what I have done is, this 1 by 2 has been taken out. So initially this equation was Im square R divided by 2 divided by t. So after substituting the value of the sin square omega t as 1 by 2 in bracket 1 minus 2 cos 2 omega t, what I have done is I have just taken this 1 by 2 outside this integration, and I am getting Im square R divided by 2t, and then I have to integrate this expression from 0 to 2t, which is in bracket 1 minus 2 cos 2 omega t dt. So I will be now solving this expression, and finally we will be able to get the average power which is dissipated over a cycle. So this is equal to integration of I will just write it here like this, from 0 to t, and it will be equal to 1 dt minus integration, and this will be in bracket. This entire expression will be in bracket, and this will be from 0, and this will be equal to 2 cos omega t dt. Okay. Now the value of this integration will be simply, it will be we can easily find it out, but now we have to find the value of this cos omega 2 cos omega t. Now so first of all, let us solve this this expression. So that is integration of, we know that is cos omega t from 0 to t dt. This can be written as sorry, this is cos 2 omega t. So this will be equal to sin 2 omega t, and what I will do is, let me just, if I take this cos, this is equal to cos 2 omega t. Now let us take 2 omega t as u. So du upon dt will be equal to 2 omega, or we can say that dt will be equal to du upon 2 omega. Okay, and the integration of this cos u will be equal to sin u. So finally we will the integration of this will be equal to will be equal to sine 2 omega t divided by 2 omega, and we will have to integrate this from 0 to t. Now we know that omega is equal to 2 pi upon t, and so if for over the average power, we have to calculate the average power which is dissipated over one complete cycle. So the value here of this will be equal to now what I here I will be doing here, that I will be substituting the value of t as 2 pi upon omega. So this will be equal to sine 2 omega into t will this t will be equal to t, so t will be equal to 2 pi upon omega. So 2 omega divided by t is equal to 2 pi upon 2 omega, and t will be equal to 2 pi upon omega. Okay, and here what I will be doing is, see, simply I'm just putting the value of t, this this small t as t. So t is here equal to 2 pi upon omega. So I have put the value of t as 2 pi upon omega and minus sine here that is equal to the sine 0. So this will be equal to sine 4 pi minus sine 0, and this will be equal to 0 because the value of sine 4 pi is equal to 0. So we can say that the integration of this expression, that is 2 cos 2 omega t dt, will be equal to 0. So simply we will be left with this expression, and now we will be able to calculate the average power which is dissipated over one complete cycle. So this will be equal to I m square r divided by 2t, and the integration of this will be equal to t, and this will be equal to from 0 to this will be equal to t, and the value of this integration, that is from of this cos 2 omega t from 0 to capital T, was as we have just found, it was equal to 0. So we finally I am getting the value of this average power as I m square r divided by 2t, and then we have to find this value, that is it will be equal to I m square r divided by 2t, and this will be equal to t minus 0. So this is equal to I m square r upon 2, because this t will get cancelled out. So the average power which is dissipated over one complete cycle is equal to 1 by 2 I m square r. Okay, now from here in the previous session we have seen that the value of Im is also equal to root 2 I, where I is the RMS value of the current. So if I substitute this value here, so I will be getting as 1 by 2 root 2 I whole square into R, and this will be equal to I square R. I square R, yes, because this root 2 will, this will become equal to 2, so this will get cancelled out, 1 by 2 into 2, and this will be equal to I square into R. So the average power which is dissipated over a complete cycle is given by I square R, where I is the RMS value of the current and R is the resistance of that resistor. So, uh, so in this session, I just wanted to discuss about two things. One was the instantaneous power. The instantaneous power is given by this is equal to I square R, and this is given as per the this value which is defined by the Joule heating, as per, because whenever there is a current flowing through a uh, resistor, the heat is dissipated, and it is given by this P is equal to I square R, and I have substituted the value of I as I m sine omega t. So this will be equal to I m square R sine square omega t, and this formula has been used as per the Joule heating effect. So the first thing was the instantaneous power which we have calculated, and the second thing was the average power which we have calculated over a time period. Means we have calculated the average power which is dissipated over one complete cycle, and this was equal to I square R, and this is I is the RMS value of the current. So thank you very much for joining in this session, and in the next session I will be continuing. I will try to come up with a couple of good questions based on what we have studied in the session number 2 and in this session. So till then, have a nice day. Bye.